Hi, this is our first video for Chapter 10, and in this video we're going to cover Section 1, an introduction to potential energy. So we're going to try to develop a better understanding of energy and how it's conserved. Let's start by recalling that forces that are generated between interactions come in pairs. If I have object A interacting with object B, that interaction generates a pair of forces that are equal and opposite, as we've discussed in our chapters covering the concept of force. There are two ways we could define a system then to think about the work that these forces do. We could define system 1 that consists of only the two particles, right? A and B, and in this case you can see that the work done in this system is external to, is coming from the environment and it's external to the system. What we would see in that case then is that force could change the kinetic energy of the system, and the total energy of the system would be, could vary as these external forces act on the system. System 2, though, includes the interaction within the system. Okay. Now we've captured both objects A and B and their exchange forces clearly inside of our system. What does this imply? This implies that the total work done is equal to 0 in this case. There are no external forces. Since there are no external forces, the external work must be equal to 0, and therefore the energy of the system energy should be conserved. But we know that, this is the same physical condition, at system 1 and system 2 are describing the same physical system. So the kinetic energy of A and B should still be changing. So what's happening? In this case, those internal forces in the system that do work are leading to a change in potential energy. Notice that these forces are equal and opposite. So as they do work on the system, the work that they do on each object A and B are going to completely cancel each other out. But what that work can do is transform the kinetic energy of the system into what we're going to call a potential energy. So potential energy we're going to think about as interaction pairs that do work contained inside of the system, and that work that those interaction pairs do can take and convert the kinetic energy into potential energy, leaving the system energy constant. And that has to be the case because there's no interaction, there's no energy flowing in our system from the environment. So if I have these two particles A and B that interact with each other, we can define the system to include the interactions between them, and then we can write down that the potential energy would be the sum of the work done on particles A and B, with a minus sign here because potential energy now we're changing as those objects take work, do work that would be taking kinetic energy out of the system, they're going to be increasing the potential energy. Okay. So it's minus that interaction work that's done on the system, where W interaction is the total work done inside of the system by those interaction forces. Okay. So the system's kinetic energy can increase if the potential energy decreases. There's some total amount of energy available in the system. If we take kinetic energy away, it's going to boost up potential energy. If we take potential energy away, it can boost up the kinetic energy. The interactions are storing energy inside of the system, with the potential to be converted at a later time into kinetic energy. So you can see this idea that in order for us to have a potential energy in a system, we need multiple objects defined inside of our system that interact with one another. And that potential energy depends on their configuration, The change in the potential energy depends on changing their configuration. Why? Because if they're exchanging some forces, I have to have them move over some distance. And so that means I'm changing the configuration between those particles inside of the system. Okay, that's going to end our first section video from the chapter on potential energy. Thank you very much.